Oh my goodness, it is the last lecture. Woohoo! Couple more things here. So first off, we're going to talk about salt hydrolysis. Ugh, God, can't even talk. I'm so excited. Salt hydrolysis. So first thing, what's a salt? No, it's not where you beat somebody up. That's a salt. What is a salt? Right? It's an ionic compound. So an ionic compound is also known as a salt. And when we dissolve ionic compounds into water, they dissociate, they break up into their ions. Those ions can act as acids or bases. Right? If I have the salt that's produced in a strong acid, strong base reaction, those don't affect the pH. So like potassium doesn't affect the pH, chloride's not going to affect the pH, sodium doesn't bother it, nitrate doesn't bother it. But what if the anion of my salt here is actually the conjugate base of a weak acid? That means that this is a weak base. So something like sodium fluoride will actually raise the pH. Potassium acetate will raise the pH because acetate is the conjugate base of a weak acid, acetic acid. We get acidic solutions when we use things like ammonium chloride because ammonium is the conjugate acid of a weak base, ammonia. All right, and there's all sorts of things that are like ammonium. They're very similar to it. All right, so those things will change the pH. So that's what we mean by salt hydrolysis. You may see that at some point. All right, common ion effect. You guys have seen this before. It's a shift in the equilibrium position that occurs because of the addition of an ion that's already involved in the equilibrium. It's Le Chatelier's principle, right? Le French guy. So imagine we have HCN. This is hydrocyanic acid, right? It's a weak acid. How do I know that? I know it because it's not one of the 7 strong acids, right? So it's got to be a weak acid. All right, so the equilibrium probably lies over here some way. Definitely not over here because it's a weak acid. All right, so we have this equilibrium set up. If I add sodium cyanide, all right, that's going to affect this equilibrium. Why? Well, it's not the sodium doing anything. It's the cyanide, the Cn minus. It's right there. And what do you guys know about equilibrium? All right, if I add something, it's going to push the equilibrium position away from the side I'm adding to. So if I add cyanide, it should push my equilibrium position back over here. So how it does that is that extra cyanide is going to consume some of this. So that's going to drop, and then these are going to go up. Right? That's what we mean by a shift to the left. Right? It's going to shift that position to the left. And so what we see is that a solution of sodium cyanide in HCN is actually going to be less acidic than the HCN by itself, right? The hydrocyanic acid by itself, right? Common ion. Oh, one last little thing here. We're going to talk about buffers. What's a buffer? A buffered solution. Those resist change in pH. They can change their pH, but it doesn't change nearly as much. So if I add like a strong acid to a buffer solution, the pH will go down a little tiny bit. If I add a strong base to a buffer solution, the pH will go up, but just a little bit. All right, the way we make these things is with weak acid and their conjugate base, or a weak base and its conjugate acid. So we use these weak conjugate pairs and put them together. All right, we get the most bang for our buck when the acid concentration and the conjugate base concentration are equal. All right, then it's going to be most resistant to changing pH. All right, so I can add either acid or base to it, and it'll kind of defend against both those things. So if all buffers resist changing pH, but not all buffers are at the same pH, right? So buffers can all have different pHs. Like I can have a buffer that has a pH of 9.5, or I can make a buffer that has a pH of 3.2, just depending on what I use to make the buffer. So how do I choose what I'm going to use to make my buffer? Let's say I need to make a buffer of pH 5.5. How do I decide what I'm going to use to make that? So we go to our handy dandy little dissociation equation here, just our generic one, right? So we take an acid, put it in water, we get hydronium and A minus. All right, so here's our Ka expression. And what I told you a second ago is for a buffered solution, we're going to have equal concentrations of the conjugate base and the acid. So this is the same. So that goes away, right? Same number. Right, it doesn't matter what they are. They go away. Math. Ta-da. So then you get Ka equals H plus. If I take the negative log of that, I get pKa equals pH. All right, so this tells me that the pH of my buffer solution is going to equal the pKa of the acid, right? So the negative base 10 log of my Ka for my acid. So I just go to a list of weak acids. I look up all the different Ka values, and I find the pKa that's closest to the pH I want my buffer to be. And voila, I am good. That's it. Holy cow. I mean, we've actually covered every topic Oh my goodness. Congratulations. You have made it to the end. It's the last video you're going to have to watch of me babbling through stuff. All right. We did it. Wahoo. It's over. All right.